angles, right? Finish triple angles. Again, for the sake of time, just jump right to the questions. Ultimately, a vector field is just a multivariate vector value function. And use the vector plot command. Then you just have to enter your components. Negative y divided by square root of x squared plus y squared. X over square root. Plus y squared, and then of course you just need intervals for x and y. Let's start minus 5 to 5. That's technically all you need. And there's our vector field. Of course, we can adjust settings. Turn off the frame, turn off the axes. Several options I can use. That's what I use. Typically use the regular option for vector points. It is the color function. Yeah, very dark color.
bunch of different options. Just make the colors one different. No, wood. There are different options. Could be rainbow, which doesn't do anything. Oh, that's lovely. Others I did my vector points as regular. Turn that off. Leave it like that. There's where I can change that. But I think they wanted it on a disk, right? Yeah, they wanted it on the disk. X squared plus y squared equals 4. Let's add that in. This element. Disk is 2. I think that should work. No, they don't like that. Yes. Okay, I literally just did what you told me to do. Because of where it's located. Oh, yeah. What I'd have to do is get rid of this. There we go. And then I can, of course, change the boundaries and everything. So boundary style. It's not going to do that, huh? I have to do region. Region boundary style. And region filling style. Let's just turn that off. And turn on the shading for the region. Nobody can do anything. Oh, good. This one's a bit more pain because it's 3D. This time it's just the vector plot 3D, and it's the same kind of idea. You have to put in your 3 components. And then give intervals for X, Y, and Z. And then you can just do a bunch of options. Box to fall, so let's set the origin. You can also make the axes, I believe. You can do axis style. Yep. Which doesn't help. Turn off that. That helps a little bit. Set those back to regular. That's just what I like. And if you don't like the 3D arrows, I know we can change that as well. There it is. Right, so just set up the arrow and you lose the 3D effect on the vector arrows. I think that's a lot better. And let's make it the standard view. Let's just kind of shift that just a little bit, maybe something like that gives a good idea. No, that looks good. Just like you can differentiate a vector value function, you can also partial differentiate vector fields. They want all the second order partials. working with vector functions, how do we differentiate a vector function?
Differentiate each component
So how do you think you're going to do a partial?
to a partial of each component.
Just take the partial of each component. In this case, first with respect to x. What's the partial of the first component with respect to x?
4xy minus 4x cubed.
Not x.
Yxy.
Y is the constant. Minus y cosine.
2x sine.
And then 2x cosine of y, right? And that's partial again with respect to x. And plus y sine of x. And then 2 cosine of y. But you could also do the partial with respect to y after the x, right? For x, xy e to the xy minus cosine of x, negative 2x sine of y, right? Yes? But we could also go down the path of partial with respect to y first. Good question. With respect to y, it's what, 2x squared? X e to the xy minus sine of x, negative x squared sine y. Again, with respect to y, zero x squared e to the xy, and what, negative x squared cosine y. Or you could do it with respect to x. For x, xy e to the xy minus cosine x, negative 2x sine of y. What do you notice?
Isn't it the same? Really? It's the same.
What's the same?
The last one?
You know what they're called?
I don't remember what they're called.
When you mix the partials?
I remember they're always the
It's
same.
just called a mixed partials.
Okay.
Mixed partials are equal. The order in which you do it doesn't matter, right? What was that called? What theorem was that?
Fubini?
Fubini's with multiple integration.
Oh.
Clairac theorem. Yeah. Clarac's theorem says the order in which you take the mixed partial doesn't matter. Fubini is the order in which you do the integral doesn't matter. And you can set up as an iterative integral. So yeah, Clarac's theorem still is valid. Now, something to point out here. How many dimensions is this vector field?
Three.
It's three-dimensional, but how many variables are there? Only two. So this is a three-dimensional vector field. However, the direction which it points does not depend on z. So yes, you can still have higher dimensional vector fields and fewer variables. We could have a four-dimensional vector field with only one variable. I mean, the direction which it points relies solely on its x-coordinate, the initial point of the x-coordinate. It's okay. Two ways to tackle this one. Could do a product rule when you do the partials, right? Specifically be the scalar multiple product rule. Or just distribute it first, perform the actual scalar multiplication first, and then take the partials. Right, remember when we were doing that with vectors? That's typically the route that I went down. I never really used product rules. Only in theory will the product rules come in handy. And I think I'm going to do that here too. I'm just going to perform the actual operation first. Let's call it a new vector. Let's call it G. Again, vector fields are just multivariate vector value functions. All the operations that we used with vector value functions are still valid. So the way that we do the scalar multiplication is the same. X squared, y squared, z squared is the first component. Then it'd be what? Negative x squared, y to the fourth z, and x, y cubed, z cubed. So let's go back. Quick comment about this topic. you're going to notice that vector analysis, what we're now doing, is going to take everything that you've done in calculus so far, Calc 1, 2, and 3, and really just put it all together. So we're going to be doing like everything from calculus here. So go back to partial derivatives. Clearly that's a third order partial. What's the order?
Z, then X. Then X again.
Z, then X, then X. That's as it's written. But does the order actually matter?
I think so.
Does it?
For a partial? I thought it did.
What did Clairwood's theorem say?
Oh, I guess if you mix it.
The order in which you take the partials doesn't matter.
Oh, okay.
So you can do that in any order you want. Right? It's written they want ZXX, but you could do XZX or XXZ. It doesn't matter. So this is where you want to be a little clever and look and go, well, that last component only has a single x, doesn't it? What's going to happen if you partial that twice with respect to x?
There's going to be 0.
So why not do that first? Then you don't have to worry about partialing it with respect to z. Because it's going to go to 0 anyway at the end. Right, now for this one, it doesn't matter. It's not going to waste that much time. But for some more complicated ones, pay attention. Pick a convenient order. So start with GX. So we can now do GXX, which gets rid of that third component. Which is just one less partial we now have to worry about. Now we can go ahead and take the partial with respect to z. That's what, 4y squared z, negative 2y to the fourth, and 0. Which equals the one that we're looking for. So nothing new right now, right? Now we enter my two favorite operations. First one, divergence. Oh wait, yeah, that's right, we had to evaluate, didn't we? Oops. Is that what, 2 minus 1, 1? Oh, that's nice, there's no x's. 4, negative 2, 0, right? as a review, what is that?
Gradient.
It's not a gradient. That would be a gradient. What is that symbol called?
Oh, it's I literally talked about it yesterday. Data mining.
Yeah, I can see how data mining is required as operator.
Yeah, for machine learning.
It actually has two names. The symbol itself has a name, and what it represents has a name. That is Nabla.
There you go.
And that character is the Nabla character, the Nabla symbol. It's the del operator. Remember that? And so you often will just hear it as del instead of Nabla. How is the del operator defined? Stick with 3 dimensions. Just how it's defined depends on how many dimensions you're in. So we'll just stick 3-dimensional. See, this makes me sad because I said this was my favorite operator, and no one remembers it. Close question on the exam. Make it worth minus infinity with 1 point. If it's wrong, negative infinity. If it's right, you get 1 point.
Oh.
That's the del operator in 3 dimensions. Technically speaking, there should be an arrow with a del too, but kind of just not. This is the divergence of a vector field. Generally speaking, symbolized as del dot f, but keep in mind you're not actually performing a dot product. Because dot product is between 2 vectors. That's an operator. So the whole thing of del dot would be 1 operator. And the reason we represent it that way it just behaves like a dot product. Partial x of the first component, partial y of the second component, partial z of the third component, sum them together. Right, so if you think of the del operator as a vector, then the divergence acts like a dot product. So that's why we represent it that way. But keep in mind that this doesn't make sense. Right, the del dot has to be out front. 4yz squared, and then plus xy squared. Measure divergence. Now for the second of my favorite operators. Oh, that's not it. Where is it? Oh, there it is. Why don't you go all the way down there? I'm going to move you up. Because I think they should be up there. This is the curl of the vector field. Red del cross F. Just curl. Again, point to note, you're not really doing a cross product, but it does behave like a cross product. That's better. So again, if you think of the del operator as a vector, it behaves just like the cross product. So you don't have to memorize those formulas if you just know what nabla is, know how dot and cross products work, you're good. So you don't have to memorize formulas. Two x y z minus negative 4y squared z 2x squared z minus y squared z. And that would be what? 0 minus 0. And I don't think that can be simplified. Right, you might be able to factor some things out, but just a little bit. Now, why do I like these operators so much? one of those. I'll do it this way then. Good. Oh, that's not good. These are four of the most famous equations in the world. Yeah, in my opinion, it's even more famous than E equals MC squared. Who studied E&M? Wow, no one's taking intro E&M at this point? That's not good. Electricity and magnetism. These are Maxwell's equations. They govern all electric and magnetic fields. Let's see, tell me what each of those are. So E is the electric field, obviously. B is your magnetic field. Rho is your electric charge density. J is the current density. So it's current. Epsilon naught is your vacuum permittivity, which is a fixed constant. It's a universal constant. And mu naught is the vacuum permeability, which again is a fixed constant. So epsilon naught in SI is about 8.85 times 10 to the minus 12. Mu naught, again in SI, about 1.26 times 10 to the minus 6. Those are fixed universal constants. Specifically, these are the differential form of Maxwell's equations. They also have integral forms, which we can't look at just yet. And funny enough, they are called Maxwell's equations, but he only came up with one. He's just the one who related them. So that first one is called Gauss's law for electricity. Second one is Gauss's law for magnetism. Then you have Faraday's law of electromagnetic induction. That's your third equation. And the fourth one is the Ampere-Maxwell law. So these really should be called Gauss's equations because he came up with two of them. But what do I know? So maybe you should remember those four equations. It's another form of Maxwell's equations because they govern light as well. The one I would like says that Maxwell said these four equations, and then there was light. So these equations are actually very important. Without these four equations, you would have no technology. None of this would exist. So, look at that. We'll do this one. So what we want to first kind of examine is this operation even defined? Well, clearly we're taking the divergence, right? Del dot. That's divergence. But you can only take divergence of vector fields. So what is that second operation?
They just multiply.
That's the gradient.
Oh.
Gradient is not a vector field. So this is defined. I'm taking divergence of a gradient. Specifically, when you take the gradient of a function, the result is called a gradient field. Does that? Let me check something. Remember what the gradient was? And then divergence. So partial x is the first. Partial y is the second. And then partial z of the third. We don't need that plus 0. But that's what we would have. Right? There are 3 proofs in there. I'll leave those for you to look at. Now let me hide that. This So the notion of potentials. If a vector field is what's called conservative, it's going to have a potential function. Let me just show that real quick. Right, function where f is the gradient of it. That's called a potential. And it's conservative if and only if the curl is 0. Right, or irrotational. Well, the first thing we want to do is let's verify that this actually is conservative. And believe it or not, a lot of forces are conservative. Gravity is conservative. The gravity force field is conservative. The electric force field is conservative. The magnetic force field is conservative. And they play a huge role in physics. That's where the whole idea of conservation of energy comes from. Actually, I think we proved conservation of energy next time. Partial z. I'm sorry, partial y of the z component. Minus partial z of the y component. Then we're going to get partial z of the x minus partial x of the z, partial x of the y, what am I doing? Partial x of the y, not partial y. Minus partial y of the x. It's conservative. What that means, there exists some function, let's call it v, such that the gradient of v equals f. Now, actually, in physics a lot, you'll see it this way. F is negative del V. Doesn't matter. But remember what a gradient is. Gradient of v would just be v sub x, comma v sub y, comma v sub z, right? So wouldn't this mean that partial of v with respect to x would have to be e to the x natural log of y? And your v sub y would have to be e to the x over y plus sine of z. And your v sub z would have to be y times the cosine of z. All three of these equations have to be satisfied. do is copy and paste them. Pick one. Your v would have to be the integral of vx with respect to x. The antiderivative. What's that antiderivative?
E to the x, ln1.
E to the x what?
ln1
Is that it?
plus c.
Uh-huh. You're not incorrect. There's going to be a constant, but it's not just c. Remember, it has to be a constant with respect to x. They have a function of y and z. Isn't that constant with respect to x? So it's plus some function of y and z. Now our goal is to find what that function is. Which one would be the easiest? Differentiate with respect to y. You get what? E to the x over y, right? Plus the partial of f with respect to y. What I'm going to specify that's strictly a function of y and z. But doesn't that have to equal e to the x over y plus sine z? Oh, look. That means that the partial of f with respect to y has to be sine of z, right? Then what's f? Just be the antiderivative with respect to y, wouldn't it? What's that antiderivative?
Sine c.
What are you missing?
Plus f x.
So first off, don't use f, because we just used f. So I'm just going to use g.
So just a constant.
Not x, because f was never a function of x. Right? F is only a function of y and z. That's why I actually wrote out y and z here, to keep it straight. Right? So just strictly a function of z would be constant with respect to y. And again, because f was never a function of x, g can't be a function of x.
Is that because we started with dx? Okay.
So here's where we're at right now. We now define that function g. Differentiate with respect to z. Y cosine of z plus g prime, right? But that has to equal y cosine of z, right? Does that mean that g prime is 0? Which makes g what? What is it? Just 0? Z?
Sorry.
So if g prime is 0, what is g? Just some constant, right? You may have been saying C, I'm just mistaken. Y sine. What's it? Yeah. Plus some arbitrary constant. Notice what this is saying then. There's an infinite number of potential functions. However, there's one thing they all have in common. Up to that constant, the functions are identical. Right? So potential functions are unique up to a constant. Much like, remember when we were doing antiderivatives in Calc 1? The antiderivative is unique up to a constant. It's the same thing. So you have a family of solutions. Right? You have a family of potential functions. But we were just asked to find a single potential function. Right? So just pick a value for say, any value will work. I pick 0, there's the potential. Right. Again, just like when we did fundamental theorem of calculus, we took what was called the simple antiderivative, which is the one where you set c to be 0. Same thing here, generally speaking. If you're asked to find a potential function, you generally want the simple potential, the one where the constant is 0. But you have to read the question, because I may ask for all potential functions, in which case you'd have to write plus c for some real number's sake. The order in which you do this doesn't matter. Right? I started with v sub x, but you could have started with v sub z and then followed a similar procedure. Or you could have started with v sub y and followed a similar procedure. Generally, pick the easiest one to start with and then go from there. Your textbook, along with a lot of other textbooks, uses a method called comparison, where they integrate each of the three and then compare them. I never really liked that method.
It still works.
It works, but it kind of makes you have to recognize patterns. Whereas this, it's just direct. You follow this procedure, you directly get to the answer. You don't have to look at three separate things and kind of go, oh, what do they all have in common? That must be my solution. Right now, this just directly gives it to you. So that's why I always stick to this method. Gradient field is another way of saying conservative field. Right? Because what is a conservative vector field? A vector field that is the gradient of some function called the potential. So they're asking to determine the values of b and c, which would make f a gradient field. I don't have time to do it, but what you would do take its curl, set it equal to 0, 0, 0 and solve for B and C. Right, because remember, it's conservative if and only if the curl is 0. You get a system of linear equations, 3 equations and 2 unknowns, you can easily solve for B and C. If I remember correctly, I actually never printed out my note sheet with this. But if I remember correctly, I think there is a unique solution. I don't think it's infinite. You get one value for B and one value for C, if I remember correctly. Those are vector fields. Again, really nothing super new. The only new thing we really did was divergence and curl. But they're still related to stuff we did previously. Maybe conservative would be the only new thing we did. The notion of conservative vector field. Any questions? That gets me back on track now. All right, so just like with the triple integrals, these will be posted, so I'll just let you read through all those preliminary slides with the definitions and stuff. Gets me back on track, which is really nice. Tuesday, we look at line integrals. Oh, joy, yes, and then after that, surface integrals. Oh, God. Surface integrals suck. So I think, yeah, that's next week. All next week is both line and surface integrals, so it's all integration next week. We're almost done, too, by the way. We only have a couple weeks left. After line and surface integrals, we look at the big 3 theorems. Like, all of calculus has been leading up to these 3 theorems. Green's theorem, Stokes' theorem, divergence theorem. This was the whole purpose of your pre-semester calculus. These 3 theorems.